OK, so now we're going to move off of vectors and talk about sort of a near cousin of vectors, or how you can deal or have vector computing in your desktop today. So this is actually, a lot of this was done actually by Ruby Lee here at Princeton. She added a lot of multimedia extensions to the HP PA RISC architecture. There's a couple other people involved in this, but she was actually pretty influential in being able to do this. The idea here is that if you have a wide register, so if you're doing, let's say, 64-bit additions, and you don't want to have to do 64-bit additions, or don't actually have 64-bit data laying around, you could cut it in half and do two 32-bit operations at the same time. Or you can use that same ALU and try to do 4 16-bits or 8 8-bit operations. So this is called SIMD, or single instruction multiple data. So you have, or short SIMD instructions here, because typically the vector length is pretty short, or multimedia extensions. And you have an instruction which says, I want to do 2 32-bit adds, we'll say, at the same time. This was popularized in x86 at least by MMX, was the first implementation of this. And it's sort of gone on from there to SSE, SSE2, SSE3, SSE4, and now Intel AVX. And the differences between MMX and all the different SSEs largely has to do with the length of the register and how many instructions they had. So in AVX, we've gone to 256-bit registers, so even wider registers, and it's extensible up to, I think, 1,000-bit or 1024 bits. One thing I did want to point out about this, which is interesting, is this requires changes to your data path. If you have an adder, and you have a 32-bit add, and now you want it to do 8-bit adds, you need to cut the carry chain in 7 places. Now that's if you have a basic adder. I guess it gets a little more complicated if you have something like a propagate or a carry look-ahead adder or something like that, because you may not have a simple place to go snip the carry chains. There is still some place to cut it, but your original design, you might have propagated across where now you need to cut the boundary. So this is definitely a challenge. Also, for things like multiplies, if you want to do 8-bit multiplies, the structure looks a little bit different there. But the big insight here is you had that logic anyway. You're just effectively adding muxes on the carry chains to the data path. And some operations you don't even need to add. Obviously, if you're operating on something like 8-bit values, you want to do the logical OR of them, you don't need to add a special instruction for that. From a implementation perspective, this is what I was trying to get at here. You have independent adds going on. They all happen in parallel. So why do we like multimedia extensions or these vector instructions, or short vector instructions? And let's compare them to our big vector machines. So one of the major differences is that you can't control the vector length. The vector length is the length of the native data word, or the length of the instruction set. Or the length of the native data type for your instruction set. And strided, scatter, gather, these other operations are hard to do, because typically you just have a single load and store, and you use the processor's load and store instructions, because the processor doesn't care. It's just like the same way that unary operations or logical operations don't need special instructions to do short vector or single instruction multiple data operations. You don't need special instructions for SIMD data to be able to do loads and stores. You just load the data and store the data. This is actually starting to change a little bit. Some of the newer versions of SSE actually do have some scatter, gather modifications. It's a little bit harder if you think about it because you can't hold a full address, if you will, in a vector. So it's not like you can actually do sort of indexes of addresses because you can't necessarily hold the full address in there. But in SSE, they've sort of come up with some way to do scatter and gather operations. Couple things about having the vector register length being limited is that you can't do as much work in one operation. So you can't necessarily do a 64 operations in one instruction like we did with our vector length of 64. So that just is a problem. And unfortunately, what happens here is you end up having to do more operations and issue more instructions, and you're effectively increasing the bandwidth out of your fetch units. So it's not as good. And finally, I just wanted to say that processors are starting to move, these multimedia extensions are starting to move a little bit towards vector processors as they add more rich instruction sets. So as we get to SSE 4, for instance, or SSE 4.2, there's more instructions in there in x86 that can do fancier things. And the vector length is even getting longer, up to 124 bits, or excuse me, 1024 bits.